For part 1a, we were looking to determine when di dt would be positive or negative. Since all the variables are positive values, di dt will be positive when ASI is greater than RI. We could also substitute the other given equations to be more specific and say that when the rate of susceptible individuals over time, or the negative rate, I should say, is greater than the rate of individuals recovering over time, we can expect di dt to be positive. For part B, we were looking to convert di dt to di ds by multiplying di dt by dt ds, or the inverse of the derivative of s with respect to t. What this allowed us to do is create a chain rule where effectively we were dividing di dt by ds dt, or ASI minus RI divided by negative ASI. When you split out the numerator, ASIs will cancel and result in -1, and then we have a second term where the i's will cancel out, and we're left with R over AS, or 1 over R naught S, as desired. For part 1c, we were looking to show that I must have the certain form as displayed in equation 6. We can do this by starting with the equation described in part B and then taking the integral with respect to s and factoring out the R naught from the second part of the integral. We arrive at the equation I equals -s plus 1 over R naught, natural log of s plus c, which is our desired equation, listed as equation 6. For part 1d, we were looking to explain why R naught equals the natural log of s as t approaches infinity divided by s as t approaches infinity minus 1. To do this, we started with our equation that we solved for in part C, and from there we evaluated I and s as t approaches infinity in order to solve for the values of c, which ends up equaling 0, and also I, which ends up equaling 0 as t goes to infinity. What ends up resulting through the math done here is that we're able to factor out R naught and divide on both sides by s as t approaches infinity minus 1, resulting in our desired statement. In part E, we were looking to describe a definition for herd immunity and identify how vaccination can lead to herd immunity. Herd immunity is when enough people become infected so that the transmission rate drops too low to sustain the virus because it has too few hosts to spread to. Vaccinating people is helpful in reaching herd immunity because it removes potential susceptible hosts and effectively moves them to the recovered category, thus eliminating the spread of the virus.
When approaching question 2, we now had to deal with the fact that recovered individuals may lose their immunity and become reinfected. So we had to introduce a proportional parameter B, which is the reinfection rate for infected individuals. So now we had to modify our original SIRS diagram, and now it becomes a full triangle, or like a full cycle, as you can see. So we have susceptible people, S going to I, infected people, I going to R, recovered people, and then recovered people going back to S now, because they're now susceptible after they lose their immunity. And to make sure that our equation was correct, we took S prime plus R prime plus I prime, we plugged it in, and we got that 0 is equal to 0, so the equation holds. For question 3a, we now had to take into account that deaths may occur due to disease, so we had to introduce the equation d prime of t is equal to I times c, where I is infected people and c is the death rate. So changing our SIRS model from the previous question, there is now 2 arrows coming out of infected people. One is recovered people, and the other one is D, which is dead people, because you can either die or recover from the disease. So once we got d prime of t, we plugged it into the original equation, S prime plus I prime plus R prime plus D prime equals 0, and the equation holds.
For part 3B, we decided to look at the Spanish flu pandemic, which was an H1N1 virus that the pre-human host was pigs. This took place in 1918 and 1919 with a death toll that reached over 50 million people. Specifically, we looked at the United States numbers, which tallied about 675,000 deaths. First, to find our A value, we had to multiply the rate of contact times the probability of transmission. And our recovery rate was about 11 days to recover, so 1 over 11 gave us an R value of 0.091. The death rate we found by taking the total number of deaths over the total number of people that were infected, which was about 0.1. And then we multiplied that by the amount of transmissions per day, which gave us an answer of 0.081 deaths per day. The infection rate was found by multiplying the rate of recovery by the infection rate. The reinfection rate was found by multiplying the rate of recovery by the infection rate. And it was also important to look at the initial conditions. So our S0 value was 103 million minus 1 over 103 million, which is very close but not equal to 1. And if you take that and add it with the I0 value, which was 1 over 103 million, that would equal 1. So the R of 0 and the D of 0 values were both 0. And our R naught we found by dividing A over R. Taking a look at the behavior of the solutions, we see that first, our recovery rate has a negative value, which is not reasonable compared to the actual data. And the number of susceptible individuals does increase at first, which is also not very realistic in terms of the actual data. But when looking at the end solutions, we see that the number of susceptible people does decrease, and the number of infected individuals does spike, obviously, and then decreases towards the end.